So this is lecture number 17. Okay. And we have been discussing about the energy stored and energy density, and energy stored in terms of D and E. And we have also discussed about the electric dipole, electric dipole, and dipole moment. We have discussed these things. Okay. Today we shall solve some problems, and then uh, we can conclude this topic before moving on to conductors and dielectrics. Okay. Yes. So let us solve one problem here. So before that, we should recall the relationships. So what all we have discussed so far. So, for example, the work done in moving a point charge, okay, that is against the field, is given by Q into E vector into uh, dl vector from infinity to that point. And if you integrate it, so if you integrate it over a distance, so that is nothing but minus Q into E power dl vector. This is joules, okay, and potential. So when charge is at origin, that is Q divided by 4 pi epsilon naught R, and Q is at origin. Okay. When Q is not at origin, that is nothing but Q divided by 4 pi epsilon naught R minus R1 dash, okay, vectors and its magnitude. Okay. And this is basically denoted as the variable quantity. The variable quantity is nothing but distance between the point of interest and the origin. So that is nothing but the R vector. Okay, this is what we have seen, and you can extend it for more number of charges. So that you can write it as so V of R vector is 1 by 4 pi epsilon naught summation of Qi divided by R minus Ri. I is equal to 1 to n, and this is magnitude. Okay, and this you can extend it for the point charge, that is a line charge. Okay, you can extend for line charge, so that is nothing but 1 by 4 pi epsilon naught integral of rho l of r dash into dn divided by r minus r dash magnitude. These things you can extend for surface charge as well as volume charge. Okay, and relationship between the field and the potential, E vector is equal to minus gradient of V. This also we have seen, and we have discussed about the energy stored in the electrostatic field. So that is nothing but WE, that is half into summation of I is equal to 1 to N Qi into Vi. This is the energy stored in the electrostatic field, and okay, and potential, and potential equation also we have discussed. So that is E due to, that is potential due to electric dipole, that is Q by 4 pi epsilon naught d cos theta by r square volts, and electric field in terms of the electric field due to dipole, that also we have discussed, that is QD by 4 pi epsilon naught r cube, and 2 cos theta ar cap plus sin theta a theta cap. This is electric field due to an electric dipole. Okay. Lastly, so we have discussed about the dipole moment. Okay, so that is moment is a vector. So E vector is given by Q into E vector, and we discussed about the voltage potential in terms of dipole moment. That is E vector into E vector along r direction 4 pi epsilon naught r square volts. Okay, this is the potential due to a dipole, and in terms of dipole moment, similarly you can express field in terms of dipole moment is Q divided by 4 pi epsilon naught r cube, and 2 cos theta ar cap plus sin theta a theta. Okay, this is what we have discussed, and we also discussed about monopole and quadrupole. Okay, and also octopole. So monopole is nothing but single point charge. Okay, where the potential varies inversely as r, and field varies inversely as r square. And in case of dipole, the potential varies inversely as r square, and field varies inversely as r cube. Okay, and multipoles, that is arrangement of dipoles, two dipoles, is called quadrupole. Arrangement of two quadrupoles is called one octopole. Okay. These things we have discussed very recently in the last class. So we shall solve some problem on these concepts, and we shall conclude this chapter. Okay. Let's take on the first problem. It's a dipole. A dipole having moment, that is P vector, is equal to 3 times into Ax cap minus 5 times into Ay cap plus 10 times into Az cap nanocoulomb meter is located at Q 1 comma 2 comma minus 4 in free space. Find V at P 2 comma 3 comma 4. Okay, so you are having the dipole and its moment is also given, that is nothing but q into d. Okay, d vector. So and it is also located at point 1 comma 2 comma minus 4. You are supposed to find the potential due to the dipole at 2 3 comma 4. Okay, so what I will do is just locate this dipole at this point 1 comma 2 comma minus 4, and I want to find the potential at this point, that is 2 3 4. So this is a dipole location. Okay, and due to this dipole, what exactly is the potential? Okay, so I'll just leave this slide for a few seconds. Please note down the question. Let us solve. Okay, so we should solve now. So let me get the formula for potential in terms of dipole moment. That is P vector into AR cap divided by 4 pi epsilon naught R square. Okay, so AR cap is nothing but R vector divided by magnitude of R vector, and R vector is equal to AX cap, AY cap, and AZ cap. Okay, so you have to find the distance vector between P and Q. Okay, so it is nothing but 2 minus 1 here in the x direction, 3 minus 2 in the y direction, and 4 minus of minus 4 in the z direction. So obviously we will get it as AX cap plus AY cap plus 8 AZ cap. Okay, its magnitude of this one is 1 square plus 1 square plus 8 square. So it is nothing but square root of 66. Okay, Okay. Yes. So now you can find AR cap. You have found out R square. You are given with P vector, that is dipole moment. Substitute the values and get me the answer. Okay. Yes. Solve for it. I'll just leave this slide for you. You have to find first one P vector dot AR vector. This unit vector along the direction of R. Find it, just multiply that dipole moment by the AR vector, and it turns out to be a scalar quantity. It turns out to be a scalar quantity, that is dot product scalar quantity. Yes. So P vector AR cap vector is 3AX cap minus 5AY cap plus 10AZ cap multiplied by, which is AX plus AY cap plus 8AZ cap divided by root 66. Okay. Yes. What's the answer you get?
So 9.6 into 10 power minus 9.
9.10
6 into 10 power minus 9.
power minus 9. Okay. So what is the unit of this one? Dipole moment. It is nothing but coulomb meter. Coulomb meter. Okay. So obviously you get this as the final answer. That is a coulomb meter, and this is nothing but nano coulomb meter. So obviously you get unit as nano coulomb meter. So potential now, it is P vector into A vector divided by 4 pi epsilon naught R square. If you substitute the values, you will get the answer. What is the answer?
So
1.307.
1.31
3.
volts, 312, something like that. I have got. So it is 1.31, something like that. Okay. Yes. So it is a straightforward problem. So if you could observe, if you know the, or if you recall some of the relationships here, then you can easily solve. Okay. And if you recall some of the concepts, then you can derive the expressions. Okay. So the basic thing remains same. That means you'll be having a point charge, you'll be having a line charge, you'll be having a volume charge, and you'll be having a surface charge. Or due to all these kinds of charges, you might experience some potentials. Due to that potentials, you might experience some moments, that is dipole moments, because of oppositely charged polarities charges, which is arranged in the space. Okay, just you have to recall the relationship, and then you can solve the problem. Okay. Yes. Next problem. find find the electric field. Find the electric field at 0 comma 0 comma 5 at 0 comma 0 comma 5 meters due to a due to a pure dipole pure dipole 1 into az cap 1 into az cap microcoulomb meter located at the origin located at the origin. So you have got dipole at 0 comma 0 comma 0. You are supposed to find the electric field at 0 comma 0 comma 5. Okay, the field is due to this dipole. So very straightforward thing, and this is in Cartesian coordinates. Just have to be careful. Okay, so we have got the expression for electric field due to a dipole. So that is given by Q into D divided by 4 pi epsilon naught R cube 2 cos theta into AR cap plus sin theta into A theta cap. So you have to convert this Cartesian coordinates to spherical coordinates first. Then only you can apply this equation. Somehow you need to convert this Cartesian coordinates to spherical coordinates. Okay, I have shared a video of that one, conversion of one form of Cartesian, one form of coordinates to another form of coordinates. Okay, so Cartesian coordinates. So x, y, z is given. You are required to find r, theta, and phi. Okay, so x is equal to square root of r is equal to square root of x square plus y square plus z square, and theta is equal to, according to that conversion, cos inverse of z by r. We don't require phi here, so that we should stop at this one. So r turns out to be 5 here, and theta turns out to be 0 here. So z is 5 and r is 5. So obviously 5 by 5 cos inverse of 1 is 0. Okay. Yes, I'll just hold this slide for a few minutes, solve for it, and get me the answer. Okay, what you got?
Sir, 143.88.
43 point. Okay, so your answer would be around 43.867, something like that, volts per meter. Volts per meter. Okay, yes. This next problem. In a certain region, in a certain region, the potential is V is equal to x square plus 3y square plus 9z. Find find E at P 1 minus 2 comma 3. I'm just revisiting the concepts again. Find E at P 1 minus 2 comma 3. So you have got V here. You have to solve for E. So which equation you will use now? You are given with potential. You have to solve for E vector. Yes, this is what we have discussed. So the seventh equation here. So E vector is equal to negative of the gradient of V. That you can use. Okay. So E vector is equal to minus gradient of V. Okay. What is gradient? What is the gradient of V? That is the next part. So what is the gradient? Can somebody tell me what is the gradient?
Sir,
Do
d
we
by v
do it?
by
Yes, dou by dou x ax cap, dou by dou y ay cap plus dou by dou z az cap. Okay, and we are using for V, and that has to be for V here. So in all the cases, you'll be right for V here. Okay. Yes. First solve this one. and then multiply by minus, you will be getting as E vector, and substitute x is equal to 1, y is equal to 2, and z is equal to 3. Quickly do it.
So minus 2ax cap
Yes, minus 2ax cap
plus 12ay cap
plus 12 or 6, just check.
12, sir.
12.
as a 12
Okay. 12
ay cap
ay cap
minus 27 az cap
minus 27
az cap.
az cap. This is total E, right?
Yes, sir.
Total E vector. Minus 2x cap plus 12 ay cap minus 27 az cap. Just check for this value, minus 27.
Sir, minus 9 AZ cap.
Yes, we have got the answer as minus 9. Just check for the value.
Yes, sir. Minus 9.
It is minus 9. So it is minus 9 AZ cap. Okay. This is electric field at T. Now you can find T. How?
Multiply by epsilon naught.
Yes, epsilon naught into E vector. Now I want you to find charge density. How to find?
Maxwell's first equation.
Yes, Maxwell's first equation. So it is gradient of E vector. Okay. So this is how. So it is coulombs per meter square and this coulombs per meter cube. You can go on finding different quantities for a given system where you know the voltage, you know the potential. Okay. Yes. Next problem. Find the work done in moving a 5 coulomb charge, 5 microcoulomb charge from origin to 2 minus 1 4 meters. Okay. Through the field, given by this equation, that is 2xyz ax cap, x squared z ay cap, x squared y az cap volts per meter, along the curve x is equal to minus 2 y cube, z is equal to 4 y square. I think we have solved one problem in this method, correct? If you could refer the previous classes, we have solved one problem on this kind, that is finding the electric field in different paths, that is work done in different paths. The work done is independent of the paths chosen, okay, provided the terminal points are same. Okay, here the points are origin and 2, minus 1, 4, and the charge is moved along the curve x is equal to minus 2y cube and z is equal to 4y square. Find the work done. So we have got the equation for work done. So what is that equation? It's minus q a to b e vector into dl vector. This is a and this is b. Okay. Yes. Your dl vector, it is simple, dx into x cap, dy into ay cap, and dz into dz cap. So some mathematical integration concepts has to be used, and the rest of the things remains same. Okay. So this problem is one for practice. Yes. Next, last concept, and we shall wind off this one. Potential due to a charged disk. Due to a charged disk. So you are having a disk. It is nothing but a circular structure. Discus throw. You can imagine that discus throw property. There is nothing but a disk, and it is a completely a charged one. So we have to find the potential at this point P, and this point P is along the axis of the disk. Somehow I need to find the potential at this point P due to this charged disk. Okay. For that, what I will do, I will choose a small region here. Okay. So it is also a circular annular ring. It is nothing but annular ring, and I will find the potential due to this annular ring at point P, and I will integrate along this complete circumference using the radius. Okay. Yes. The radius of the disk is r, and let the radius of the annular ring is z, and distance between O and P is x. Therefore, the distance between this point and point P, it is square root of z square plus x square. Z square plus x square. Okay. So why I am just using this small ring? Because I can integrate to find potential to the entire disk, because I know the radius of the disk. Okay. So we got the equation. It is V is equal to Q by 4 pi epsilon naught r square. So this is nothing but Q, and r is the distance here, this point to this point. So that is nothing but z square plus x square. Now I want to find Q. So Q in terms of the surface charge density, I can write it is rho s by A. Okay. So rho s by A, area of the ring, it is nothing but 2 pi r, and the thickness of the ring, I am taking it as dz. Okay, that is thickness of the ring as dz. So it is nothing but rho s by 2 pi r dz. I think I made a mistake here. Rho s is equal to q by a, I suppose. Yes, rho s is equal to q by a. Rho s is equal to q by a. So it is q here. Okay. So q, and this is rho s, and this is rho s. So therefore, you got to know q. That is rho s into 2 pi r into dz. Okay. So using this expression in the potential expression, you might solve for it. That is V is equal to Q by 4 pi epsilon r square. So Q is equal to now 2 pi r, that is 2 pi z, sorry, it is nothing but 2 pi z, that is the radius of the angular ring, is 2 pi z into dz into rho s divided by 4 pi epsilon naught square root of z square plus x square. So this is for the annular ring. For whole disk, it is 0 to r, is rho s into 2 pi z into dz divided by 4 pi epsilon naught z square plus x square. If you just simplify it, and assuming that x is larger than r, okay, you'll be getting it as 4 pi epsilon naught x. Assuming that x is very much greater than r. A small derivation is there. I just leave it to you. So this is potential due to a charged disk. Okay. This is 2 pi z. I have to use this as 2 pi z plus angular ring I'm considering. So the radius of the angular ring is z instead. Yes. Okay. So what you can expect in this concept or in these topics, you can expect uh, the derivation for electric field in terms of potential, it is and energy stored in the electrostatic field, and work done, the expressions. Okay, and also you can expect the potential due to a dipole, or potential due to a quadrupole, or potential due to a octopole. Expressions you will have to derive. Okay, and based on these derived expressions, so what all problems I have discussed in my regular classes, that is sufficient. So I'm majorly covering the topics from Basavaraju. Okay, S.P. Basavaraju. Okay, that is field theory by S.P. Basavaraju. Just go through those concepts because it's clearly explained. Okay, yes. If you got any doubts, you can ask me, or else I will just stop at this point. And tomorrow, uh, I'll be taking two sessions, one during the lab and one during the morning sessions. Okay, and I will start the conductors and dielectrics and capacitances. From that topic, there will be mm, small derivations here and there, and those derivations are very simple if you have understood these kinds of derivations. Okay, yes, I will just stop at this point. If you have got any doubts, you can ask me, else you can leave.